Let's try looking at how the pressure varies with height in fluid statics from a little more common sense point of view. We have no motion. Consider a little box like this, oriented vertically with the sides all vertical, and it contains a certain amount of mass, and that mass will be subject to a gravitational force acting downwards of the mass times gravity. If nothing's moving, then the only thing to offset that will be the difference between the pressure on the top, which will act with a force of pressure top times area top, offset by, in the upwards direction, a pressure force acting on the bottom. Pressure on the bottom times the area on the bottom. Now, if the gravitational force is acting downwards, this upwards pressure force must be larger than this downwards pressure force on the top. And thus, if the areas are the same top and bottom, then the pressure on the bottom must be higher. So if we do a vertical force balance, we have the pressure on the bottom times the area on the bottom acting upwards, minus the pressure on the top times the area on the top, minus m times g, all equal to 0 in order to have no acceleration. Now, if the area on the bottom is equal to the area on the top, and both of those we just say are equal to A, and the mass is equal to the density times the area, the cross-sectional area, times the height, delta H, that's how tall this control volume is, then we wind up with P bottom minus P top equal to rho g delta H. Or in the form we're going to use over and over again, delta P equals rho g delta H. Remember, pressure increases as you go downwards, and you need to be careful with your sign convention. So check those signs to make sure you're getting your pressure variation in the right direction. Notice also that delta P equal to rho GH tells us that the density is going to be very important to the pressure difference. And the density of water is around 1,000 kilograms per cubic meter, whereas the density of air is around 1.2 kilograms per cubic meter. So that's about an 800 times difference. And because of that 800 times difference, you'll see that delta P in gases may be small for small elevation changes, while delta P in liquids will be much larger. The end result is, although I don't see a very significant pressure change in the air as I go from the bottom floor of a building up to the third floor, I'll see a substantial change in pressure in the water as I go from the surface of the water to 10 meters below the surface. Whether you use this explanation of the way pressure changes with elevation in fluid statics, or use a more rigorous explanation based on the Navier-Stokes equation, the bottom line is that the pressure goes up as you go down in elevation, and it goes up as rho g times the change in elevation. And we can use that in all sorts of situations to figure out what the pressure is at different locations in a fluid.